Imagine this. The year is 2084. A sleek silver spacecraft, far more advanced than anything we've ever built, silently glides through the cold, endless void of interstellar space. It's heading toward Proxima Centauri b, a distant exoplanet, over 4 light-years away, where astronomers believe liquid water might exist. Inside the spacecraft, the hum of powerful fusion engines fills the cabin, a sound not of combustion, but of controlled atomic fire, mimicking the same process that powers the sun itself. This ship is moving at a speed once thought impossible. Not in thousands of years, not in centuries, but in mere decades, it will reach another star. This isn't a scene from a sci-fi movie. It's a glimpse into a future we're trying to build today. And the key to making it happen, fusion energy, the very same force that fuels the stars, may soon be the driving power behind humanity's greatest leap into the cosmos. But how close are we to turning this vision into reality? And why is fusion power considered the holy grail of space travel? To understand that, we first need to take a step back and look at one of the biggest challenges of space exploration: energy. Since the dawn of the space age, we've relied on chemical rockets to escape Earth's gravity and explore the cosmos. The mighty Saturn V rocket that took astronauts to the moon in 1969 burned through an astonishing 95% of its total mass just to generate the thrust needed for liftoff. This is the harsh reality of chemical propulsion. It requires enormous amounts of fuel, which makes deep space travel incredibly inefficient. While this method has served us well for reaching nearby destinations like the Moon and Mars, it becomes completely impractical when we start thinking about interstellar voyages. Consider this. Even with today's most powerful propulsion systems, a spacecraft traveling at its fastest possible speed would still take over 70,000 years to reach Proxima Centauri. That's nearly 3 times longer than the entire span of human civilization. Clearly, if we want to explore the stars within a human lifetime, we need something far more advanced. This is where fusion energy comes into play. Unlike chemical rockets, which burn through their fuel in minutes, or even nuclear fission engines, which are limited by radioactive waste and efficiency constraints, fusion propulsion offers a way to generate continuous, powerful thrust without the need for massive fuel tanks. Instead of burning fuel, fusion reactors work by forcing atomic nuclei together under extreme heat and pressure, releasing millions of times more energy than traditional chemical combustion. And the best part? The primary fuel for fusion, hydrogen, is the most abundant element in the universe, meaning our spacecraft could potentially refuel by collecting hydrogen directly from space itself. But how does this work? Imagine a fusion-powered spacecraft, a sleek high-tech vehicle with a glowing blue plasma engine at its rear. Inside the engine, hydrogen atoms are heated to temperatures exceeding 100 million degrees, creating a swirling, ultra-hot plasma. This plasma is then confined by powerful magnetic fields, forcing the hydrogen atoms to collide and fuse into helium. In this moment of fusion, a tremendous burst of energy is released, energy that can be converted into high-speed plasma jets, propelling the spacecraft forward with incredible efficiency. With this method, a fusion-powered spacecraft could theoretically reach speeds of up to 10% the speed of light. That's nearly 67 million miles per hour, fast enough to reach Pluto in just a matter of weeks instead of decades, or to travel to the nearest star system within 40 years instead of thousands. For the first time in human history, true interstellar travel would no longer be a dream, it would be a possibility. Of course, turning this concept into reality isn't as simple as flipping a switch. Controlling a fusion reaction requires technology far beyond anything we currently have. On Earth, scientists have been working for decades to achieve what's known as net positive fusion, where the energy output is greater than the energy required to sustain the reaction. Projects like ITER in France and the National Ignition Facility in the US are already making tremendous strides toward this goal. In December 2022, scientists at the National Ignition Facility achieved a historic breakthrough, producing more fusion energy than was used to trigger the reaction for the first time ever. While these experiments are still in their early stages, They represent a turning point in our quest to harness the power of the stars. So, what's next? If fusion can be mastered on Earth, how do we take it to space? What would a fusion-powered spacecraft actually look like? And how would it change the way we explore the universe? Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. But we're only scratching the surface. The real magic happens when we start designing spacecraft that use this revolutionary technology. In the next section, we'll dive deep into how fusion engines could transform space travel, the engineering challenges that still need to be solved, and what the future of interstellar missions might look like. Picture this. A fusion-powered spacecraft, 20 times the size of the International Space Station, is stationed in low Earth orbit. Inside, a crew of astronauts, scientists, engineers, and pilots prepares for a mission unlike any before. Their destination? Titan, Saturn's mysterious ice-covered moon. The mission would have taken over 7 years using conventional propulsion, but thanks to fusion energy, they'll get there in less than 100 days. As the countdown begins, the ship's fusion reactor roars to life, igniting a brilliant blue plasma that swirls inside the magnetic containment chamber. Then, with a flash of light, the spacecraft accelerates, leaving Earth behind, heading deeper into the cosmos than any human has ever gone before. This is the promise of fusion propulsion, an engine capable of delivering not just power, but unparalleled speed, endurance, and efficiency. But how exactly would it work? Let's break it down. A fusion rocket engine operates on the same principle as a fusion reactor, but with a crucial difference. Instead of generating electricity, it converts fusion energy directly into thrust. The heart of the system is the magnetic confinement chamber, where hydrogen isotopes, deuterium and tritium, are heated to temperatures exceeding 100 million degrees Fahrenheit, creating an electrified gas known as plasma. Powerful. Superconducting magnets keep this plasma suspended, preventing it from touching the reactor walls and instantly destroying them. As fusion occurs, the reaction releases an enormous amount of energy, which is then directed out of the spacecraft as a high-velocity plasma jet. But here's the real game-changer. Unlike chemical rockets, which burn fuel in an explosive burst, a fusion engine provides continuous acceleration. That means a spacecraft wouldn't just coast through space after an initial boost. It would keep speeding up, reaching velocities impossible for today's technology. This constant acceleration is key to reducing travel times to distant planets and eventually to other stars. Let's put that into perspective. A traditional spacecraft, like NASA's Voyager 1, which launched in 1977, is currently traveling at 38,000 miles per hour, one of the fastest human-made objects in history. But even at that speed, it would take 75,000 years to reach Proxima Centauri. With fusion propulsion, a spacecraft could reach 10% the speed of light, slashing that journey to just 40 years. Suddenly, interstellar travel is within the realm of possibility, not for distant future civilizations, but for ours. Of course, engineering a working fusion spacecraft comes with huge challenges. First, there's the issue of fuel availability. While deuterium is relatively abundant, found in ocean water right here on Earth, tritium is rare and radioactive, making it difficult to store and transport. Some researchers propose using helium-3, an isotope found in trace amounts on the Moon, and possibly in the atmospheres of gas giants like Jupiter. Mining these elements from space could eventually fuel a solar system-wide economy, where fusion-powered spacecraft hop between planets, refueling as they go. Then there's the problem of heat management. Fusion reactions generate temperatures hotter than the core of the Sun. Keeping a spacecraft from melting under these extreme conditions requires cutting-edge thermal regulation. Think radiators the size of football fields designed to dissipate heat into space. Some concepts, like the direct fusion drive, DFD, being developed at Princeton Plasma Physics Laboratory, use superconducting coils to channel heat away efficiently, turning it into additional thrust instead of waste energy. And Finally, we need to consider magnetic containment. If the powerful magnetic fields keeping the plasma confined were to fail, even for a fraction of a second, the entire fusion reaction could destabilize, shutting down the engine or worse, damaging the spacecraft itself. That's why researchers are experimenting with tokamak designs and stellarators, advanced magnetic confinement systems designed to keep the fusion reaction stable over long durations. Despite these challenges, the future of fusion-powered space travel is closer than many realize. NASA, the European Space Agency, and private companies like Helion Energy and TAE Technologies are racing to develop the first operational fusion reactors, with some promising designs expected to be tested in space within the next 20 to 30 years. But fusion propulsion isn't just about speed, it's also about sustainability. Imagine a future where Mars isn't a one-way trip, but a thriving colony with regular fusion-powered transport ships bringing supplies and people back and forth. Picture a world where deep space mining operations harvest ice from Europa or methane from Titan, fueling entire missions with resources found off-world. Fusion technology could make all of this a reality, transforming space from an unexplored frontier into an extension of human civilization itself. But what would a fully functional, fusion-powered interstellar spacecraft actually look like? How would astronauts live and work aboard such a vessel? And what kind of missions could this technology unlock that were once deemed impossible? A lone astronaut stands at the edge of a massive observation window, gazing out at the endless darkness of space. Outside, a swirling blue jet of plasma flares from the spacecraft's fusion engine, pushing it ever closer to its destination, an uncharted exoplanet orbiting Alpha Centauri. The ship is unlike anything humans have ever built before, a city-sized structure designed not just for exploration, but for survival. This is humanity's first true interstellar voyage, and it's made possible by the most powerful propulsion system ever conceived, fusion energy. But what would such a spacecraft actually look like? What kind of technology would it need to carry, and how would it sustain human life on a journey lasting decades, or even centuries? To answer that, let's step inside and explore the inner workings of a fusion-powered interstellar vessel. The Cree. First thing you'd notice is its sheer size. Unlike the compact, fuel-limited rockets of today, a fusion spacecraft would be a vast, modular structure, designed to accommodate not just propulsion, but also life support, radiation shielding, and scientific research. Some designs propose ships several kilometers long, with massive rotating sections to simulate gravity, ensuring that astronauts don't suffer the severe muscle and bone loss that comes with prolonged exposure to weightlessness. At the heart of the spacecraft lies its fusion reactor, a glowing, pulsating core where hydrogen plasma is trapped inside a powerful magnetic field, continuously fusing atoms and releasing an immense amount of energy. The fusion engine itself would be mounted at the rear, directing superheated plasma exhaust out into space, propelling the ship forward at unimaginable speeds. Unlike chemical rockets that burn fuel in a single explosive burst, this engine provides constant acceleration, allowing the spacecraft to gradually build momentum over months or even years. But propulsion is just one piece of the puzzle. Life support is just as critical. Unlike a short trip to the Moon or even a multi-year mission to Mars, an interstellar journey would require closed-loop ecological systems capable of sustaining a crew for decades, perhaps even generations. The spacecraft would need massive hydroponic farms growing fresh food and recycling oxygen through carefully controlled ecosystems. Waste would be repurposed, water purified and reused endlessly, every resource meticulously managed to ensure survival in the void. And then there's the issue of radiation. Beyond Earth's protective magnetic field, deep space is filled with high-energy cosmic rays that could damage human DNA and increase cancer risks. Traditional spacecraft rely on thick aluminum shielding, but for an interstellar journey, something more advanced would be needed. One idea: using the ship's own hydrogen fuel as a protective barrier. Hydrogen is an excellent radiation shield, meaning that by surrounding crew compartments with fuel storage tanks, the spacecraft could effectively block dangerous cosmic rays, keeping the crew safe for long-term missions. So now we have a fusion-powered vessel capable of sustaining a crew and protecting them from space's harshest elements. But what missions could this technology enable? What new frontiers could humanity explore with a spacecraft that doesn't need to worry about running out of fuel? One possibility is the establishment of permanent human colonies beyond our solar system. With fusion propulsion, a ship could carry entire habitat modules, deploying them on distant planets that show signs of being habitable. Imagine a mission to Proxima Centauri b, a potentially Earth-like exoplanet orbiting our nearest neighboring star. Instead of robotic probes sending back grainy images, humans could walk on its surface, study its atmosphere, and search for signs of alien life firsthand. Fusion spacecraft could also revolutionize deep space scientific exploration. Imagine deploying massive telescopes beyond the Kuiper Belt, free from the interference of Earth's atmosphere and light pollution. We could build floating research stations on Titan, studying its methane lakes up close, or send submarines beneath the icy crust of Europa, searching for life in its hidden ocean. But perhaps the most mind-bending possibility, a generation ship, a vessel so large and self-sustaining that it could support multiple generations of humans, embarking on a voyage lasting hundreds or even thousands of years. These ships wouldn't just be transportation, they'd be floating civilizations, carrying the seeds of humanity to new worlds, ensuring that our species survives long after Earth is gone. Of course, there are still significant hurdles to overcome. Before we reach this future, the technology behind fusion propulsion is advancing rapidly, but we're still in the early stages. Achieving net positive fusion on Earth is a challenge in itself. Scaling it up for use in space adds another layer of complexity. And then there's the question of cost. Building and launching a fusion-powered spacecraft would require international collaboration on an unprecedented scale, possibly even a level of resource sharing between nations that humanity has never attempted before. But if history has taught us anything, it's that the greatest discoveries are made by those willing to take risks, to push the boundaries of the impossible. In the past, humans believed that crossing an ocean was a death sentence, that flying was a dream, that landing on the moon was a fantasy. Yet here we are, having achieved all of these feats in just a few centuries. So the real question isn't whether fusion-powered space travel is possible. The question is, when will we make it a reality? And who will be the pioneers that take that first interstellar journey? 100 years from now, a child stands on the observation deck of a massive space station orbiting a distant exoplanet. She presses her hands against the glass, staring in wonder as a fusion-powered starship ignites its engines in the darkness, preparing to embark on a journey to an even more distant world. This isn't science fiction, it's the future we are on the brink of building. And it all starts right now. The dream of fusion-powered space travel is no longer just an abstract idea, it's a technological race unfolding in real time. Across the world, scientists, engineers, and space agencies are pushing the boundaries of what's possible, making breakthroughs that could bring this revolutionary propulsion system to life. But how close are we really? And what will it take to get there? Let's start with where we stand today. Right now, the most promising developments in fusion research are happening in laboratories dedicated to achieving net positive fusion, where the energy produced from a fusion reaction exceeds the energy needed to sustain it. In December 2022, the National Ignition Facility, NIF, made history by achieving this milestone for the first time, proving that fusion power isn't just a theoretical concept, it's an achievable reality. Meanwhile, private companies like Helion Energy, Commonwealth Fusion Systems, and TAE Technologies are racing to develop commercial fusion reactors, aiming to deliver usable fusion energy within the next 2 decades. But how does this translate to space travel? Well, organizations like NASA, the European Space Agency, ESA, and the US Department of Energy are already investing in the idea of fusion propulsion systems. The Direct Fusion Drive, DFD, developed by researchers at Princeton, is one of the most promising designs. This system would use a compact tokamak-style reactor to generate a continuous stream of high-speed plasma, providing sustained thrust without the need for massive fuel tanks. If successful, the DFD could cut travel time to Mars from 6 months to just a few weeks, and push even further into the solar system without the need for refueling. But here's where things get really exciting. Scientists are already designing the first fusion-powered space missions. One concept, known as Project Helios, proposes sending a fusion-powered probe to the outer solar system within the next 30 years, using experimental fusion engines to test their capabilities in deep space. Meanwhile, DARPA's Draco program is working on nuclear thermal propulsion, a stepping stone toward fusion-based systems that could one day power crewed missions beyond Mars. The next few decades will be critical. If fusion reactors on Earth reach commercial viability, the next logical step will be miniaturizing them for space applications. This means developing lightweight superconducting magnets, ultra-efficient, plasma confinement systems, and thermal shielding that can withstand the extreme conditions of deep space. It won't be easy, but the rewards are staggering. Once we crack fusion propulsion, the entire universe opens up to us. So what happens when we finally build a fusion-powered starship? What new frontiers will it unlock? In the short term, we'll see rapid expansion across our solar system. Mars will no longer be a once-in-a-lifetime mission, but a routine destination. Missions to Jupiter's moons, Saturn's rings, and even the icy depths of Neptune will become feasible within a single astronaut's career. Imagine a world where fusion-powered cargo ships transport raw materials from asteroids, fueling an off-world economy that spans the inner solar system. In the long term, interstellar travel will shift from fantasy to a serious engineering challenge. Concepts like the Breakthrough Starshot initiative, which aims to send tiny fusion-powered probes to Alpha Centauri within a human lifetime, could evolve into fully crewed starships capable of reaching habitable exoplanets. If a ship could reach even 10% the speed of light, the dream of becoming an interstellar species would be within reach. But this isn't just about technology, it's about us. Every great leap in human history, from the first ocean explorers to the Apollo moon landings, was driven not just by science but by visionaries who dared to dream beyond their own horizons. Fusion energy is the next great horizon, a power source that could free us from the limits of Earth and take us to places we've only imagined. So the question is, are we ready? The future of space travel isn't just something that will happen on its own. It's something that will be built by people who are alive right now, scientists, engineers, dreamers, and visionaries who refuse to accept the limits of today as the boundaries of tomorrow. The first fusion-powered spacecraft hasn't been built yet, but it will be. And when it launches, it will mark the beginning of a new era for humanity, one where the stars are no longer distant points of light, but destinations we can reach. So, what do you think? Will fusion propulsion be the breakthrough that takes us beyond our solar system? Could we see a crewed mission to another star in our lifetime? Let us know your thoughts in the comments. And if you found this video fascinating, hit the like button and share it with others who love the mysteries of the universe. The more we discuss, the closer we get to making this future a reality. Until next time, keep looking up. The future is waiting.